Okay, so let us now start solving the next set of exercises which involve the notion of subgroups. And this is the first one. Exercise 33. In each case, is H a subgroup of G? There are three parts. In the first one, G is this group. The general linear group consisting of 2 by 2 non-singular matrices over the field of real numbers. That means 2 by 2 matrices with real entries which have non-zero determinants. And the operation is of course matrix multiplication, and H is the unimodular matrices, I think, yes, the set of matrices with determinant 1. And the second one, G is the dihedral group D10 and H is the set of flips, reflections. And in the third one, G is the group of all rational numbers under addition of rational numbers, and here H is the subset consisting of those rational numbers A divided by B, where A and B are integers and 2 does not divide B, the denominator B. So let's see what the solution turns out to be. So we need to figure out whether this H is a subgroup of G. In order to show that H is a subgroup of G, which is in fact the case here, H is, you will see H is a subgroup of G. To prove that, we need to show three things. First, the identity element of this group is in H. That means the identity element, which is what? The 2 by 2 identity matrix. We need to show that that matrix is an element in H. That is the first thing. The second thing is that if we take two elements from H, say matrices A and B, then their product AB should belong to H. And the third thing is that A inverse should also belong to H. So let's show these things one by one. We have determinant of the 2 by 2 identity matrix equal to 1. We already know this fact. So that means it's the unimodular matrix. It's a matrix with determinant 1. So this will belong to H. Okay, so the H here, it satisfies the first criterion for being a subgroup. Now let A and B be two matrices in H. That means what? That means A and B are 2 by 2 real matrices where the determinants of both of them are equal to 1. Then determinant of A is equal to determinant of B is equal to 1. Hence we have, now we know, or we can easily show that the determinant of the product AB is equal to the product of the determinants. I say we can easily show, or if someone is not so sure about this property, that is because we are having here only 2 by 2 matrices. So determinants have a very simple formula. If your matrix is A, B, C, D, then its determinant is just this real number, AD minus BC. So using this definition, you can clearly show this, and in a quite straightforward manner. Now, because A and B are both having determinant 1, so this determinant also now is going to be 1, because the first one is 1 and the second one is also 1. So this is equal to 1. And we also know, or in fact one can show this as well for non-singular matrices, that the determinant of the inverse of A is the ordinary reciprocal of the determinant of A. And in this case that is also equal to 1, because the denominator here is 1. This implies that both the product AB and the inverse A inverse are now elements in H. Both of them belong to H, and hence H now satisfies all the criteria for being a subgroup of G, so it is a subgroup of G. So the first subset turns out to be a subgroup of G. Thus, H is a subgroup of G. Then we come to the next one, the dihedral group D10, which recall that it is the group of symmetries of a regular pentagon, a regular five-sided polygon, and H is the set of all flips that are symmetries of the polygon. Okay, the pentagon, five-sided polygon having all side lengths equal. Now, is this H a subgroup of G? It turns out that this H is not a subgroup of G. The simple reason is that the first criterion itself is not satisfied for H, or not satisfied by H. That is because what is the first criterion? It says that the identity element in G should belong to H. That is the first criterion for subgroup. In this case, that is not the case. That is because the identity element in G is what? It's that operation which you can view it like this, rotating the pentagon about its center through an angle 0 degree. Or more simply, you can view it as doing absolutely nothing to the pentagon. And flips which are reflections about some axis, they do something to everything, any geometrical figure. A flip never is like the identity. The identity does absolutely nothing to a geometrical figure. Any flip actually does something. So that's why the identity in G is not in H, simply because it is not a flip. So, and that is why H is not a subgroup of G. 2. We write directly like this: H is not a subgroup of G since the identity element in G is not a flip. This much is enough. Okay, so that is the second subdivision. Now the third one. Now there is a problem with the third one. The question itself is not well posed. The H here, there is no problem with this group. We already know that the set of rational numbers forms a group under ordinary addition of rational numbers. That there is nothing wrong with that. But the H that we see here is not well defined for a peculiar reason. Let us see why. H actually does not make sense. At first sight, it may not be apparent that there is something wrong with H. But if you look carefully into the conditions that define H, you will find that there actually is a very big problem. Because quotients are involved, you may think that, well, I can immediately see a problem. The problem being that in these conditions, it is not mentioned that B should be non-zero. Although that is not explicitly mentioned here in these conditions, but in fact B here actually is non-zero due to the presence of this condition that 2 does not divide B, because 2 divides 0. So this condition that 2 does not divide B ensures that B cannot be 0. That is not the problem, that is there. So B is non-zero, but the problem is this. You think of the rational number 2 divided by 3. I think I already need ink. Give me a moment. Okay, so you consider this rational number 2 divided by 3. So A and B, you have 2 in place of A and 3 in place of B now. Both 2 and 3 are integers and the denominator 3 is not divisible by 2. So fine. So 2 divided by 3 should belong to H, because all the conditions are satisfied for this rational number. But a rational number can be expressed as a ratio, I should not say ratio, but as a quotient of 2 integers in not a unique way, but actually infinitely many ways. For example, this same rational number 2 divided by 3 can also be written as 4 divided by 6. They are the same rational number because you can cancel 2 out from the numerator and denominator. However, if you use this expression, the rational number which is there in the background it can be expressed as 2 divided by 3, and that same thing can also be expressed as 4 divided by 6. But now you look at this, 4 and 6 are also integers. 6 is of course non-zero. But now 6 is divisible by 2. Here, however, 3 is not divisible by 2. So what do you do? I mean, according to these criteria, 4 divided by 6 should not be in H. However, if you use this expression, which actually denotes the same rational number, it says that 2 divided by 3 should belong to H. So that means there is a very big problem with these conditions. These conditions actually do not define H in a well-defined manner because of these things. So let us address this issue first. We need to redefine H so that it becomes well defined, and then we can see whether that slightly different H is a subgroup of this G or not. In fact, we make this issue a part of the solution. 3. Since a rational number can be expressed as a quotient of integers in more, we don't need to mention in infinitely many ways, more than one is enough. H is not well defined. In this, because of specifically this reason, H is not well defined. Note that two divided by 3 is equal to 4 divided by 6, but by the definition of H, this belongs to H, whereas this does not belong to H. So we modify H by redefining it as follows. Okay, so now we are going to write the new H, where these conditions will remain, but we are going to introduce one extra condition which will make sure that this problem does not arise. We are now going to define H like this. A divided by B, where A and B are still integers, and this time we are choosing B to be a positive integer. That can always be done. I mean, if you have, for example, have something like this, you can always write in its place minus 2 divided by 3. If you have a negative denominator, you can replace that with its positive counterpart, and you can transfer the minus sign to the numerator. That can always be done. So no matter what you have, you can always make the denominator conveniently positive. The denominator, of course, cannot be 0, so it is either a positive integer or a negative integer. If you do have negative, you make it positive. That's just it. So any rational number, in fact, can be expressed in this form where the denominator is a positive integer. The numerator of course will take care of the sign of the rational number. If it is negative, then the numerator will take the burden of making it negative. Fine, but that is not enough. We of course also have this condition that 2 divides b, but I will write that afterwards. Let me just now put the crucial thing first, that a and b are relatively prime and 2 does not divide b. If according to this definition, however, that possibility of expressing a rational number as a quotient of 2 integers in more than one way, that does not occur here. These conditions make sure that every rational number r can be expressed in this form where all the conditions are satisfied in a unique way. Okay, so that means normally see there is nothing called the denominator of a rational number when you express it as a product of as a quotient of 2 integers, because for a given rational number denominator is not unique, so you cannot say the denominator. Here however you can say, because you can in fact show this, that if say you have a rational number which has been expressed in this form where a and b satisfy all these conditions, and also at the same time it can also be expressed as a quotient of 2 possibly other integers c and d which also satisfy these conditions, that c and d are of course integers where d is positive, c and d are relatively prime and 2 does not divide d, then you will be able to show that a is equal to c and b is equal to d. So in that sense this expression now is unique in this new definition of h, which however is actually not the previous h, it's a new h. So if you want you can give it a new name also, which I won't do. Okay, so uniqueness part, this part I leave to you. It is very easy to miss this issue with h. That's because if you just simply apply the criteria to show that h is a subgroup of G, the fact that there is this problem with h, that does not affect the arguments. So you will end up showing that h is in fact a subgroup of G, but h itself is not well defined, so that means it's not a set at all. Okay, however now with this h things are okay, so I urge you to actually prove that thing, okay, that the expression now becomes unique and we don't this type of problems don't arise now with this new h. Now we show that this new h is in fact a subgroup of Q, that is G. We have so the first criterion is that the unit element, the identity element in Q is in H, because it is not 1, sorry, I was thinking about multiplication. This is a group under ordinary addition of rational numbers, so the identity element is 0. 0 belongs to H, so that is the first observation. Since you can write 0 as 0 divided by 1, we won't say anything more than this. You have to see that in fact this is the only way of expressing 0 as a quotient a divided by b satisfying all these conditions. Let us see whether the conditions are actually satisfied. 0 and 1 are of course integers, 1 is a positive integer, and GCD of 0 and 1 is 1. Also 2 does not divide 1, so yes, so that is why 0 belongs to H. Now let and C divided by D belong to H, then now we cannot write like this. Simply saying that A divided by B belongs to H, for example, does not automatically imply that A and B are integers like that. Why I am saying that is because, say, you may say something like this also, no? 4 divided by 6 belongs to H, for example. 4 divided by 6 actually belongs to H, our new H. Do you see why? That is because this rational number 4 divided by 6 in this representation is not one of these representations. Expressing 4 by 6 like this requires us to get rid of common factors so that the GCD of the numerator and denominator becomes 1. So we have to have 2 divided by 3, and then we can see whether these 2 and 3 satisfy these conditions or not, and they do. They are integers where the denominator of course is positive. They are relatively prime. Their greatest common divisor is 1, and 2 does not divide 3. So the problem that we previously had now does not arise, because we will not use 4 and 6 to decide whether this belongs to H or not. We will reduce it, get this ultimate reduced form, and then we will decide using this criteria. So instead, let us write like this. Now let this belong to H such that A, B, C, D are integers, B and D are positive, GCD of A and B is 1, which is also equal to the GCD of C and D, and 2 does not divide B, and also 2 does not divide D. Okay, so now we can say that yes, these are already in this form because that's how we have chosen them. Now we need to show two things, that the sum of these two is again an element in H, and the product of these two, no, what am I saying? Product will not appear. Sum of these two elements is in H, and the negative of any one of them is also in H, because the operation is addition, so multiplication does not arise. Now or then A divided by B plus C divided by D, this can be written as AD plus BC divided by BD. Now AD plus BC and BD may have a common factor greater than 1. Okay, in other words, the GCD of AD plus BC and BD may not be equal to 1. That possibility is there, but we can always cancel common factors and reduce this fraction in a form where it looks like this. There exists integers, say E and F, such that F is positive, 2 does not divide F, GCD of E and F. Oh, okay. Wait, we cannot just simply write this 2 does not divide condition now. There exist integers E and F using which you can express this quotient as E divided by F, where E and F are relatively prime. F is positive and it's just that. Okay, this condition has to be separately, it has to be concluded in fact, and that will make this thing an element of H. GCD of E and F is equal to 1 and BD is equal to E divided by F. This part I hope you understand. It's like saying something like this. Say you have 4 divided by minus 6. Say this turns out to ultimately be this 4 divided by minus 6. So what now we are saying is that you can express this in a form as a quotient of 2 integers, maybe some other 2 integers. The denominator is positive and those 2 integers are relatively prime, and of course the 4 divided by minus 6 becomes that thing divided by that thing, and those 2 things in this case are minus 2 and 3. So think of 4 divided by minus 6 in place of AD plus BC divided by BD, and this is E minus 2 and F is 3. This you will always find. And why we get a positive denominator, I have already said how to get positive denominator. If you have a negative denominator, just transfer the minus sign to the numerator. And you can always cancel common factors. So ultimately you will get numerator and denominator which are relatively prime. Okay, now comes this non-divisibility criterion. We cannot just simply say that 2 does not divide F. We have to prove that. Suppose two divides F. Okay. Then F is equal to 2k for some positive integer because the F itself is positive. Okay, now what do we get from this equation? If we cross multiply, we then have AD plus BC times F, that is equal to E times BD, or AD plus BC times 2k Now what can we say from this final equation? Has anything gone wrong? We are expecting for something to go wrong because we have supposed a thing which we want to show does not happen, namely this. So we are expecting a contradiction. Now, do we have any contradiction from this last equation? Note that all the things involved here are integers. So question of divisibility comes. Since the left hand side is a multiple of 2, the right hand side should also be a multiple of 2. In other words, the right hand side should be divisible by 2. Okay. Thus 2 divides E times B D. Since 2 is a prime number, we must have two dividing E or 2 dividing B or 2 dividing D, because primes have that property. If a prime divides the product of a number of integers, then it has to divide at least one of them. These two, however, can be immediately ruled out because B and D already are integers which are not divisible by 2. That is because A by B and C by D are coming from our newly defined H. Since we already have two not dividing B and two not dividing D, it must be the case that 2 divides E. That's the only possibility. But now see what has happened. 2 divides E and 2 also divides F. So 2 is a common divisor of E and F. So it has to divide the greatest common divisor by a property of GCD. Thus 2 should divide the greatest common divisor of E and F, which however is 1, and this is a contradiction. So that means this supposition is wrong. 2 cannot divide F. We have now proved that. It just does not simply immediately come simply from the fact that this quotient can be expressed in this form. No, it comes out as a consequence of all the other things. Okay, so now where are we? We have shown that this can be expressed in this form where these conditions are true, and also this condition is, or rather its negation is true, that 2 does not divide F. So we write that thing now. Hence, but before that we of course have to write the conclusion. So our last supposition is wrong, i.e. 2 does not divide F. We thus have A by B plus C divided by D equal to AD plus BC divided by BD, which is equal to E divided by F, where E and F are integers, F is positive, E and F are relatively prime, and 2 does not divide F. Now we have all the conditions for E by F to be an element of H. Two does not divide F. Hence, this is where we may choose to not write this thing in the middle. This belongs to H. So this shows that the sum of any two elements in H is again in H. The next thing that we have to show that the negative of, say, A divided by B is in H, that is very simple. Also, this is, of course, it can be written as minus A divided by B, where minus A and B are integers because A and B originally were integers. B is positive, B was originally positive and it stays positive because we haven't done anything to B. We have moved this minus sign with A. GCD of minus A and B is also equal to 1 because A and B originally had their GCD equal to 1, and when we calculate GCD, signs do not matter, signs do not affect anything. That is because the greatest common divisor of two integers when it exists is by definition a positive integer. And that condition is still, it persists, that 2 does not divide B. Hence, the negative of A divided by B, it looks awful. This also belongs to H. So now we can finally say H is a subgroup, and having done so much, you should not forget ultimately that this H is that new H, okay, not the H that is given in the text of G. So that is the 33rd one. Next, the 34th one. Here also it's same. In same means similar. In each case is HA subgroup of G. Is it really that thing again? Yeah, but now the groups and the subsets are of course different. And the first one, G, is again that Dihedral Group D10, and now H is the set of rotations. In the previous one we considered the set of all flips or reflections. Here now H is the set of all rotations. That is the other type of symmetries of a regular pentagon. You rotate a regular pentagon about its center, or more specifically about an axis that passes through the center of the pentagon and is perpendicular to the plane where the pentagon is lying through some specific angles, and those operations are the symmetries of the pentagon, and those rotations now we are talking about. H is the set of those rotations. So that is the first one. The second one is again the group of rational numbers under addition, and H is the set of non-negative rational numbers. And what about the third? G is the multiplicative group. This time they are considering again the set of rational numbers with without zero. G is the, and the operation is multiplication. Multiplicative group of non-zero rational numbers. And H is the set of all positive rational numbers. So this next one, let's see the solution. Unlike the set of flips, the set of rotations will turn out to be a group. The reason is simple. Since the identity element of G in G, same thing, is the rotation through 0 degree, through an angle 0 degree. It is a rotation nonetheless. So that is why it is in H. In H. Also, for any two rotations, say R1 and R2 in D10, we clearly have R1, R2 and R1 inverse in H, which just simply is another way of saying that both these elements, one of them is R1, R2 and the other one is R1 inverse, are themselves rotations. You can clearly understand why. say R1 is rotation through an angle, R2 is rotation through a possibly different angle. R1, R2 is the combined rotation through that angle, which is the sum of those two angles. That's just it. And if R1 is a rotation in the anti-clockwise direction through some angle, then R1 inverse is the clockwise rotation through that same angle, absolute value of that same angle. So both these things are rotations, so they belong to H. Hence H is a subgroup of G, which is D10. Then the second one, H is the set of non-negative rational numbers, and G as usual is the additive group of rational numbers. This one is not a subgroup. H is not a subgroup of G, since for example 1 belongs to H. 1 is a positive integer, so it is also a positive rational number, but its inverse, which is -1, it does not belong to H because it's a negative rational number. So inverses don't exist. In fact, there is only one element in H which also has its inverse in H, that is the rational number 0, which in fact there is in H has that. That is because we have non-negative, okay, not strictly positive. But anyway, it is not a subgroup. And then the third one, G is the multiplicative group of non-zero rational numbers, and H is the set of positive. This one will be a subgroup. We have the non-zero rational numbers, we already know, form a group under multiplication of rational numbers, where the identity element is the number 1, is the integer 1, and that one of course belongs to H because it's also a positive rational number. Let R1 and R2 be two elements in H. Then R1 and R2 are both positive, strictly positive rational numbers. Then R1, R2 are positive rational numbers. There is really no need to again write, because you see here we are repeating things. R1 and R2 being in H is equivalent to the statement that they are positive rational numbers, but I want to emphasize the fact that they are positive rational numbers. I want to see these things in front of my eyes, so that what I am now going to write next, that becomes something that we already know. Then the product R1, R2 and the inverse, which in this case is the reciprocal because the operation is multiplication of R1, are also positive rational numbers, i.e. R1, R2 and 1 over R1 both belong to H. Hence, H is a subgroup of G. Okay, so this solution is also over. Next, the next one is about dihedral groups in general. For each positive integer n greater than or equal to 3. Why do we need to mention positive separately? If it's an integer greater than or equal to 3, it's automatically positive. But anyway, determine the center of the dihedral group D2n center of D2n. British spelling, okay, not American, CENTER. You write whatever you are comfortable with. Okay, so we want to find the center of the dihedral group D2n where n is an integer at least 3. Now its solution is in fact available at the end of the text because odd numbered exercises have their solutions available in the text. So this one I want you to go through the solution and see what the author has written. I will in fact tell you the final answer, but you have to go through what Lee has written at the end of the text and try to understand how one obtains this thing that now I am going to write. The thing is this: if n is odd, then the center of the dihedral group D2n, it consists of only the identity element in our group D2n, which is a rotation through an angle 0, and that is denoted by this notation R0. It's there in the text. So when n is odd, this is the center. Oh, if, not in. And if n is even, then the center is non-trivial and besides the identity element there is this thing also, rotation through an angle 180 degrees. So you see what the author has written, and if you do not understand something, you can of course always ask me. This exercise is there in Herstein's topics in algebra also, and we have already gone through it. Same exercise. Next, you can find that exercise, I think, if I am remembering correctly, at the end of the section titled Homomorphisms in Herstein's topics in algebra. Anyway, so it's available in this text also, so you don't have to go through Herstein. Okay, the next one, show that the center of the, again, general linear group consists of matrices of this form. Consists of what does Lee write? Consists of matrices that look like this. This type of matrices are known as scalar matrices, which are diagonal matrices where all the diagonal entries are equal. And because we are in general linear group, so we also want simultaneously the determinant of this matrix to be non-zero. So that is why we need A itself to be non-zero for all 0 not equal to A belonging to okay, I remember something. You see, Herstein is very casual in, at least in writing that text known as Topics in Algebra, to the point that some statements are simply wrong if one thinks about it. In this situation, while writing this condition that A is a non-zero real number in symbols like that, what Herstein would do is this. It becomes frustrating, but that's just how, I mean, you understand what he is trying to say, but what he is writing is simply wrong. In place of this, Herstein would write something like this. Okay, it really does not make sense, because we are not using the symbols in a very nice order so that the statement itself makes some sense. This is in fact what you should write. So Lee has carefully written it here that A is a real number which is non-zero, not that A is not equal to 0 and 0 is a real number. Okay, so now we need to show that the center of this general linear group is the set of scalar matrices, which of course are non-trivial. Sorry, I mean not non-trivial but non-singular. So to figure out the structure of a matrix in the center of this group, we take any matrix in the center and see what we have. So let this matrix belong to the center of the general linear group. That simply means that this matrix commutes with every matrix in this group. So we can now use this to our advantage by picking some specifically chosen matrices and using the fact that this matrix will commute with them to figure out what conditions we can have that A, B, C and D, these entries must satisfy. Then A, B, C, D, I in fact have done the calculation here, so let me just at least see what are the matrices that will help us. Then this product will be equal to that other product where we interchange the positions of the matrices. Now what will this product be? A plus 0, A, 0 plus 0, 0, C plus 0, C, oh we are getting C here, okay, no problem, and 0 plus 0, 0. Now this thing should be equal to another matrix which is this product. Now what is this matrix? A plus 0 A, B plus 0 B, and of course because this second row is 0, the others will become 0. Okay, so these two matrices are equal. That means what? The first row, first column entries of course are actually the same thing. This, however, the first row, second column entries tell us that B should be equal to 0. Similarly, C should be equal to 0, which implies B equal to 0 equal to C. Hence, ABCD, our original matrix, is actually a diagonal matrix because the off diagonal entries must be 0. But we are not quite there. We want to next show that A and D are in fact equal. So let's now see how we can show that then. And for that one, we are again going to use the fact that our ABCD, which now is, it turns out that it's a diagonal matrix, it still commutes with everything. So in particular, it will commute with another such matrix where all the entries are 0 except this one, the first row, second column entry. Next, we have A00D 0100. Now what is this product? 0 plus 0 0, A plus 0 A, 0 plus 0 0, 0 plus 0 0. This should be equal to a matrix here which is equal to this other product by interchanging the matrices. 0 plus 0 0, 0 plus D D, 0 plus, and this one is 0, second row is 0, so here also all the entries will be 0. Okay, now from this equality we can directly see that A should be equal to D, which implies A is equal to D. Hence, our original matrix, which we previously reduced to this form, it can now be further reduced, and it turns out that it's not just simply a diagonal matrix. In particular, it's a scalar matrix. But we are not done. Note that we have just simply shown that any element in the center of this general linear group must be a scalar matrix. But what about the other way? Are all scalar matrices actually there in the center? In other words, now we need to show that in fact all scalar matrices or rather I should put it this way, any scalar matrix commutes with all elements in the general linear group. Now, for any element in the you look at these two products, alpha, beta, gamma, delta. Let's just use the space freely. A alpha plus 0 gamma is A alpha. A beta plus 0 delta is A beta. 0 alpha plus A gamma is A gamma. 0 beta plus A delta is A delta. So you can see that the effect of this multiplication, multiplying this matrix by this scalar matrix, is the same as multiplying the original matrix, this matrix, by the scalar A, and that is why it's called a scalar matrix. So this is one thing. And now what happens if we change the order? Alpha A plus beta 0 is alpha A, that is the same as A alpha. 0 plus beta A, that means A beta. Gamma A plus 0 is A gamma, and 0 plus delta A delta. They are the same. Okay. Hence, the center of the general linear group consists of non-singular scalar matrices. Okay, so that's just what we wanted to show. I cannot, of course, possibly complete all the solutions in this video itself. Let's do one more. Okay, we will continue in the next Lee update. This one will be what? 37. Show that the intersection of two groups of G is also a what? Of two subgroups, okay? Intersection of two subgroups of a group G is also a subgroup of G. And then the generalization. Then extend this to show that in fact the intersection of any number of subgroups, finite or even infinite, is again a subgroup if Ni is a subgroup of G for every I coming from some set T index set. T, then show that, we have already written show that, then the intersection of all the n i's as I varies over T is a subgroup of G. I will show only this part, the first one, that the intersection of two subgroups is a subgroup, and this extension is absolutely straightforward, as straightforward as things go. So I will leave that to you. So let's see the two subgroup case. Let H, K be two subgroups of G. Okay, we need to prove that their intersection is a subgroup. Then, because they are subgroups of G, they are groups in their own right and they are subsystems in G. So each one of them will contain the identity element in G. So E belongs to H and E belongs to K. E is the identity element in G, which implies that E belongs to their intersection. So the intersection in fact satisfies the first criterion for being a subgroup of G. Next, consider two elements in the intersection, say A and B, belong to this. Then A and B both belong to H as well as both belong to K. Since H, K are subgroups of G, we have both AB and A inverse belonging to H, and at the same time this is the consequence of the fact that H is a subgroup of G. Just like that, because K is a subgroup of G, these elements also belong to K. Hence, both of them belong to the intersection of H and K. This shows that H intersection K is a subgroup of G. Now whatever you see here that have been done to H intersection K, You then have to do exactly all the things similarly for this general intersection, where the number of subgroups is equal to the number of elements in T. And for the sake of logical consistency and for the sake of avoiding unnecessary logical complications, consider this T to be a non-empty set. Okay, T may be infinite, but don't take T to be the empty set, because in that case there is a problem. When defining intersection of a collection of some sets where the collection has been indexed by some index set T from where the labels are coming, I values are coming, that T is taken to be non-empty. If you take it to be empty, then there are some pretty nasty logical problems that arise. So to avoid those things, take T to be non-empty, and please complete this. In fact, we haven't completed it, we have just proved the first part. And then of course in the next Lee update we will continue with the other exercises, their solutions. So that being said, this is all for tonight. If you want to say if you have any doubt, anything else you want to say regarding these things, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. And tomorrow we again have real analysis, where hopefully we will complete the ongoing set of exercises, so that we can go in the next analysis video to infinite series and study their convergence and whatnot. So that's just it for tonight. So see you tomorrow with real analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.